And here we are, it is the physics video lecture. Physics 105A, video lecture 5. So I had a couple of questions about the end of the third lecture, and I'll just start with that little heads up. So this is about an expression d dt of f of r of x of t, y of t, z of t. I probably hadn't written it out this much, but I had just mentioned something about the chain rule. So the chain rule for multivariable calculus would be the following. So what we're looking at here is f is a function of a scalar. We're talking about r being the root x squared plus y squared plus z squared, okay, just the magnitude of the position vector. We are in Cartesian coordinates right here. So if we were to do this thing, we'd actually have to do, first of all, f prime of r, but then our chain rule would tell us to take dr dx and dx dt. And we would have to repeat that 3 times. Okay. Then we'd have f prime of r, dr, dy, dy dt, r. And we're actually going to do a bit more of this later in the semester and next semester. So the chain rule and functions of many variables, very important in mechanics, dy dt. So if we had done that, and of course we could also use a summation convection and say we'd have x sub 1, x sub 2, and x sub 3, but we'll leave it explicit like this. We will then have common to all of these f prime of r, but this dr dx, y and z dotted in, or multiplied by these x, y, and z derivatives, that is clearly a dot product. So that would be gradient of r, okay, r is a scalar, but its gradient is a vector dotted into the velocity, and we've learned to write that r dot. So completing this exercise, the gradient of r would be a unit vector in the direction of r, and then we would have the dot product here. Okay. So I just kind of scrawled that up there, and you can just add this to your notes. We'll do more about chain rule in multivariable calculus later. Good. So that, just to clarify any ambiguities that were there. Next, I want to do as an application to our coordinate systems that we've introduced and the velocities and accelerations and such, I want to do just the pendulum, the simple pendulum. So we'll start with its free body diagram. Something you guys have seen, I'm sure. Here, let's make a nice big picture here. So we've got a pendulum of length L. It's got some little bob mass M on the end. And it's going to be motion in the plane. And we want to do the free body diagram. Okay, so it's going to swing back and forth. Oh, I should maybe say we've got an angle phi here. So phi equals 0 is straight down. Gravity pointing straight down. And if we do a free body diagram, we can say, well, there is the weight, and the only other force is this tension here. So that's a tension. but let's talk about our coordinate system. We know that, let's go ahead and draw sort of a circle that this thing can move around. And so we know there is a phi hat and there is an r hat coordinate system. So that's how they attach to the pendulum. Okay, gravity straight down, there's our angle phi equals 0, r hat and phi hat. So now we want to write Newton's law. Well, Newton's law, we have mass times acceleration is equal to the net force, and we're going to translate this into the r hat and phi hat components of plane polar coordinates. So in plane polar coordinates, with the vectors, we would have an r hat vector and a phi hat vector. The left side of the equation would be m r second derivative minus r phi dot squared. That's mass times acceleration equals, I'm just going to say the r hat component of the force, and in the phi hat component we'd have m 2 r dot phi dot plus r phi second derivative would be f in the phi direction. I'll just work on the right side of the board here. So we want to translate this, and we're going to say that here r is equal to L is equal to a constant. So all the derivatives of r, like r dot r second derivative, go away. We translate that into here, let's see what we have. So for this r hat equation, we have minus m L phi dot squared is equal to, now we need the forces in the r hat direction. Well, r hat is pointing out, so the tension is opposite it, so that's minus tension. And this mg, let's go ahead and place where that angle phi is. Okay, we've got phi there and there. So this mg cosine phi is pointing in r hat direction. So plus mg cos phi. So far so good. What about this differential equation here? These are all vanishing. M, L, we have M, L, phi, second derivative, equals, and now we have this mg along the phi hat direction. Well, minus phi hat is in that direction, so it's going to be minus mg sine of phi, okay? So again, these are the differential equations, Newton's law, in terms of these basis vectors, r hat and phi hat. So finally what I'll do is discuss both of these. Okay, the first equation up there, we're going to solve for the tension. So we find tension is equal to mg cosine of phi plus ml phi dot squared. If you look at this and consider it for a moment, you'll see that this is the famous expression mv squared, in this case over L. That's the centripetal force expression. Okay. Now, the other differential equation, we're going to just cancel m on both sides. Phi second derivative is equal to minus g divided by L sine of phi. So this is the one we would actually have to solve. It's a differential equation of one quantity, phi, and in fact, since it's the pendulum, I'll just even complete this little project. Let G over L equal omega naught squared. It has nothing to do with phi dot. That's going to be the oscillation frequency. Sine of phi approximately equal to phi for small, I'll just write for phi much less than 1. For phi much less than 1, that's called the small angle approximation. And having said that, we have phi double dot equals minus omega naught squared phi. That is the equation of the harmonic oscillator. Works for a pendulum. We'll have a lot of opportunity to study this. I just wanted to set that up. Okay, so yeah, that's how you go from these coordinates into the differential equation. This is a completely standard simple harmonic motion differential equation. Okay, so I can use this to segue into our next topic. Namely, we are going to study motion in one dimension and in terms of one variable differential equations. Even though this motion takes place in the plane, this is also a candidate for study. Okay? So our next topic is Newton's law in one dimension, or we could say Newton's law with 1 degree of freedom. So next, one-dimensional problems. And this is going to occupy us for quite a while, because it's going to be a pretty rich. So one-dimensional problems, or Newton's law in one dimension, or we could also talk about systems with 1 degree of freedom. Systems with 1 degree of freedom. So I'm going to set this up as general, as we need. And what we're looking at, there's Newton's law up there. We're looking at systems with this form. Mass times 2 derivatives equals a net force. I won't write net here anymore. I'll just say the force. And the force can be a function of position, of velocity, and of explicit time. So that's what we're going to study. And this is pretty rich because it includes many different types of systems. Okay, so forces that are purely a function of position are going to be of study, but we can also have forces that are purely a function of time, forces that are explicitly purely a function of velocity, or any combination of these. What we need is some example systems. So force a function of position, velocity, time. That's fully general. So we'll just work our way through a number of examples of this. And And in fact, the first example is one that we've already done. We'll just put it in here. That is when the force is equal to a constant. So examples, F is a constant. So that's, for example, the free fall problem that we've talked about. Then we have is equal to some constant. And if we integrate twice, and to not lose sight of the fact that it is a force, we'll just call it F0, and we can integrate twice, okay? Then we've got F0 over m for our constant acceleration, and we've actually solved constant acceleration problems. And x of t is equal to x0 plus v0 t plus 1/2. There's our acceleration, t squared. Okay. And v of t is dx dt, etc. So that's the first kind, and there we did. We took care of that. The next one we want to do, oh, and by the way, this is really the prototypical solution, so we haven't done anything trivial here, but we'll see limiting cases can always be taken in terms of this, and we could substitute F naught over m for constant acceleration if we don't want so many letters. But let's immediately do a second example where f is explicitly a function of t, why not? Okay, so f of t is going to be f0 e to the minus alpha t. Okay, so this is a decreasing, we'll just say t greater than or equal to 0. So this is a function where the force decreases to 0, starts out equal to f0, decreases to 0. So how would we solve this here? We would have m dv dt, right? That's the second derivative. Go ahead and write it out. So first derivative of velocity, m dv dt is equal to f naught e to the minus alpha t. Actually, you know what, for these comparison purposes I'm driving at here, let's go ahead and remind ourselves this would be v0 plus f naught over m t. Okay, that would be, that's the v of t. Because we're going to go ahead and solve this, and then we're going to take a certain limit. Okay. E to the minus alpha t, and now we just have to take an antiderivative. So we have dv dt is equal to f naught over m e to the minus alpha t minus alpha t dt, and we can do a prime here, dt prime 0 to t. So when I say t prime, it's just an integration variable. There's the actual t of the function. Over here, since we're going from 0 to t, but these two cancel, we could actually say we have integral dv v naught to v, and put a v prime there. So yeah, we're going to get v minus v0 on the left side. On the right side, we've got f naught over m, and we have to do this derivative here. We have 1 over minus alpha e to the minus alpha t prime evaluated 0 to t, we have f naught minus f naught over m alpha. So we pulled that out and we have e to the minus alpha t minus 1. Okay. So I'm going to rewrite that and then we'll showcase it. Good, so let's send this up here. So continuing directly underneath, you see we have v of t is equal to v0, and I'll just flip this around, plus f naught over m alpha 1 minus e to the minus alpha t. Okay, this is already a little more complicated than this one here. But it's an exact solution, and if you take the derivative of this, dv dt, you're going to get this f naught over m alpha minus another minus from the inner derivative. It's going to come out, okay? So that's the correct solution. Now here's a technique we have to learn, and it's part of the way of thinking that a physicist has. The next question here is, what about the limiting cases? So first of all, we checked the equation. We checked the differential equation, and we just can see by inspection when I take the derivative here, minus and minus, bring down the alpha, cancels that one. So we're good. So we checked the equation, and then initial condition. Well, when t is equal to 0, this cancels, and v is equal to v0. So we've got the initial condition as well. Right, the initial condition, t equals 0. But now the question is, what about the limiting case? Now, the limiting case, here we are, of alpha going to 0. When alpha equals 0, it's just a constant force. And the constant force problem we already solved. So this is the really important, I'll put a star here, limiting case, alpha goes to 0. It's going to be a thing we do all semester. When we're doing a problem, we want to get the limiting case and find the simple one that we already know. Okay, very important. So limiting case alpha goes to 0. Let's put a box around here. It's a great problem. Simple as it is. What we see is we can't just set alpha equal to 0. Now there are different ways of taking the limiting case. You may use L'Hopital's rule. Alpha goes to 0. But you're going to have to do something to do the limiting case alpha goes to 0. Because we need Taylor expansions a lot this semester. I'll discuss it in terms of that. For small alpha times t, we've got e to the minus alpha t is equal to 1 minus alpha t. Then you've got plus 1 over 2 factorial alpha t squared minus 1 over 3 factorial alpha t cubed, and so forth. That would be the series expansion of this exponential. We just need this linear case right here in order to work this out. So let me go ahead and erase this right here. And we will have v of t, I'm just going to write approximate v0 F naught over M, 1 minus, and now I'll do this F naught over M alpha, 1 minus alpha t plus and so on. And you can see what's going to happen here. 1 minus 1 is a 0, minus times minus is plus. I'm going to have alpha t. That alpha is going to cancel that one. So we have v naught plus f naught over m t. And the higher order terms that I've left out of here, they are going to be, they're always going to have another power of alpha, okay, and powers of t as well, but I'm just going to write plus some function that is of the order of alpha, okay, because it's going to be alpha, alpha squared, alpha cubed, etc. So in the limit alpha goes to 0, we have v of t is equal to v naught plus f naught over m times t. Check. Okay, so that is satisfying. I'm going to leave a task for you guys. Now everything's up here that we're going to need to do this next, and I'll put this as a homework assignment. Namely, take this result, carefully integrate it one more time, and then first of all get the answer, and second thing is to test the limiting case. So let me write here homework. So the homework problem is going to be to integrate star equation star to obtain x of t. Okay, that's the first thing. And very important, when you integrate the way I did here, do the same thing for x. You know, get x minus x naught on the left, and then you'll integrate this thing up here with respect to time and go from 0 to t. Okay. If you do that, you won't have you will not have any undetermined integration constants. It'll come out exactly analogous to what I did right here. So you'll get x equals x0 plus this other stuff. And then the next thing we're going to do, it's going to look a little worse than this one, is do the limit as alpha goes to 0. So let's go ahead and number these. 1 and 2. Take limit alpha goes to 0 of x of t, and what you want to do is obtain this x of t up here. Okay, so you do that carefully. It's a couple more steps because you have to go into your exponential with one more of these. Okay, go with your exponential up to here. A couple more steps and you will obtain it. So obtain, yeah, I just name everything with a star, so you got to pay attention here. Right now this is double star. Okay. So yeah, that's a elementary problem. F was a function of time explicitly, and we have this parameter here. When alpha goes to 0, this just has to turn into a 1, and we have to get that equation back again. I'm going to consult the clock here. Great. Let's see what else. There is another limiting case of interest, namely alpha goes to infinity. Okay. If alpha goes to infinity, it looks like this gets wiped out, and then in this denominator, everything goes away. Alpha goes to infinity, v is just equal to v0. The reason is for sufficiently large alpha, this exponential decreases so rapidly that this force in essence never existed. It never, it had some finite value for some infinitesimal time. It's not enough to get anything done. So that's actually an interesting limiting case as well. Good, so that was function of time of that type, and we're going to move to another type of problem. Since I've now done this, MdV dt, I actually have another example to go. Okay, let's send this up. And I'm going to erase these, but we'll keep these in mind. Those are our limiting cases for a number of one-dimensional problems. Okay, so 1, 2, I think I'm on 3. We have m equals f. I'm going to leave it unspecified. What I want to do now is write dv dt, which is what this second derivative is equal to dv dx times dx dt, just by the chain rule. But this itself is v, so this is v dv dx. So we can write Newton's law in one dimension as m v dv dx is equal to f. And in this case, I'm going to write it f equals constant equals f naught equals constant. Okay. So what we have is v dv dx is equal to f naught divided by m. And we can integrate both sides of this with respect to x. Okay. So we're going to have integral v dv dx dx equals f over m integral dx. We can even go x0 to x on this side, and once we cancel these dx's, we can have v0 to v prime dv prime, since it's just an integration variable, equals f naught over m x minus x0 on the right. So if we do this integral on the left, that's just 1/2 v prime squared from v0 to v. And you can see what we're going to get. Arrow, we're going to get v squared minus v0 squared. I'm going to take that 2 and cross multiply over. It's 2 times a x minus x0 with acceleration is f0 over m. So I did that because that's the missing one-dimensional constant acceleration kinematics equation that I didn't have initially. So yeah, we have that here. There are other ways to obtain it, but in keeping with what we're doing now, we're going to go ahead and do it in this form here. So this is also a technique to keep in mind. There are interesting problems where we make this transformation from this form of the acceleration to this one. And at this point, we've eliminated the time. So this is the type of problem where you eliminate the time, and of course the solution here also eliminates the time. Okay, good. So there's a result that we have. Let's do maybe one more. Check the clock again. Yeah, we'll do one more interesting problem here. Good. Okay, this time, since I'm numbering things, 4. And just to remind us, we already have, f equals constant, f equals f of t so far. Next, now f equals f of v. So what's a good velocity dependent problem? Well, my example is going to be free fall with friction. Example, free fall with velocity dependent friction. Okay. So that's an important rule actually. Friction laws are actually pretty complicated. The velocity dependent friction, I should say, note for slower speeds, for smaller velocities. Because there is a linear law for smaller velocities and there's a quadratic law for larger ones and so forth. Good. So let's go ahead and imagine we're dropping that tennis ball and we've got the weight and we've got a friction force. And we're just going to say it's equal to minus, or magnitude-wise, it's just equal to B times V. So that's a linear friction law. And free body diagram, now I'm going to even put the positive direction down here. I'll put the positive direction down. And now we have m dv dt, that's the acceleration side. And the net force side is equal to mg minus b times v. And that can be turned into dv dt is equal to g minus b divided by m times v. So there's a differential equation for free fall with friction, and we're looking at positive direction down. So here again, we can even say, what about the limit of b goes to 0? It should just be free fall with the positive direction down. We can just write that down right away. Okay. On the other hand, if the entire right side of the equation turns into 0, then we would have constant velocity. So that would give us the terminal speed. So we can actually say things about this equation without actually even solving it. So let me go ahead and put these as some notes. B goes to 0, then it's just free fall, which is constant acceleration, which is constant force that we already had on the board. G minus B over mv goes to 0. Then we would say V is going to V terminal is equal to mg divided by B. And we would have a terminal speed because if the right side is 0, then the acceleration is 0. And this terminal speed is a constant velocity, constant speed. Okay, but having said all that, and this is an example of how you can do a physical interpretation or analysis of your differential equation before you even solve it. Okay, but now we are going to solve it. And the solution of this uses a technique called separation of variables. So we're going to solve this equation. Once again, call it star. Solve equation star using the separation of variables. Separation of variables. Separation of variables. And this technique means we say dv over g minus b over m times v is equal to dt. Okay. We're going to integrate both sides, 0 to t, and here we're going to integrate from v0 to v. This technique will leave us no undetermined integration constants. Yeah, let's see. Anything else? The proof of this technique is actually not difficult to do. I may supply it later, or you guys could try to supply it yourselves. How if you integrate this up on both sides, and you define an inverse function, and then you differentiate it, and you get this equation back again, which is the proof that what we have is a solution. But let's just go ahead and take it at face value for the moment. We just separated, treating this as a ratio, and so forth. Now, what do we get on the left side? We're looking at a natural log. So I'm going to write natural log of g minus b over m. That's b over m b prime, b naught to v. And let's see, if we took the derivative, we'd have negative b over m. So we'll go ahead and put in front here negative m divided by b. And on the right side we have t. Okay. We can also write natural log of g minus b over mv divided by g minus b over m v0, and then we'll take this over to the right side, minus b divided by m times t, and then we can exponentiate. Now it's always good to be in this form right here, because the argument of the log is dimensionless. I'm going to do one more step on this. So as long as we're keeping the argument dimensionless, we can do some of our algebra inside the argument there, rather than later. So we can also say the natural log of mg divided by b minus b divided by mg divided by b minus b0 equal minus b over mt. And now we'll do the exponential of both sides, and we get mg. In fact, while I'm at it, why don't I do the minus here and the plus here, right? I can do that as well. I just multiply top and bottom by minus 1. So now we have v minus mg over b, exponentiating both sides, equals v0 minus mg divided by b times e to the minus b over m times t. And this may, yeah, we could go ahead and v of t equals m times g divided by b plus b0 minus m times g divided by b e to the minus bt over m. And I consult the clock one more time. We may pick this up next time. Yeah, we're going to want to discuss this at greater length. So what I'll do next time is put this up on the board. Put this here. I'll just say a couple words about it. One thing you can see if you just look at your t equals 0 initial condition, this turns into a 1, these two cancel, v equals v0, so you've got the initial condition here. You could take the derivative and you'll get the original differential equation. But one thing you can't do is just put b equals 0 into here. You can't just put b equals 0 into here and get some result. Okay. And yet we know that when b is equal to 0, we're supposed to just get your basic free fall without friction. So we're going to, again, discuss this thing as its limiting case. And, you know, just to remind myself, I'll put this as a homework at some point in time. Check limit b goes to 0. In fact, a couple more of these, and we're going to spend some time doing Taylor expansions, just because it's so useful. Okay, but for now, we've got this. We could, you know, we could integrate it again to get x of t, and then we could investigate these limits as b goes to 0. This, we're no longer seeing things the way we did before. One more thing that we are seeing though, in the limit as time goes to infinity, this exponential, of course, gets rid of this whole term. So as time goes to infinity, we do find, did I have it up there on the board anymore? We do find that terminal speed. Okay, so we did find that already. Okay, good. We're going to leave it here, pick up next time. See you guys next time.